Let's talk about conservative vector fields now. So we'll focus on two types of vector fields, those in 2D and those in 3D. So 2D vector fields are when f is equal to pi plus qj, where p and q are just like functions. And in 3D, f is equal to pi plus qj plus rk. Yeah, p, q, and r are just functions. If a vector field is conservative, there exists a scalar function, or just function, f, such that the vector field will be equal to this function's gradient. In that case, once you find this scalar function, then you can say that cf dot dr is equal to c gradient f dot dr, which is equal to f of r of t1 minus f of r of t naught, assuming c goes from t0 to t1. So I have two examples, and both of these vector fields, 2D and 3D, are conservative. I'm going to show you how to prove they're conservative, and if they are, how to evaluate integrals knowing that the vector field is conservative. So here's a 2D example. Let's say we have a vector field, f is equal to 1 plus xy times e to the xy in the I direction, plus x squared e to the xy in the j direction. So this test, the conservative test, is to see if dq dx is equal to dp dy. If it is, then this vector field is conservative. So dq dx is equal to, well, I'm going to label my p and q here. So dq, so this is 2x e to the xy plus x squared y e to the xy. dp dy is equal to x e to the xy plus 1 plus xy times x e to the xy. This is equal to 2x e to the xy plus x squared y e to the xy. dq dx is equal to dp dy, so this means this vector field is conservative. So now let's find the scalar function f of xy. Let's find out what f of xy is equal to. So p is equal to fx, so p is equal to fx, which is equal to, I'm going to expand this bracket, e to the power of xy plus xy e to the xy. And let's integrate this with respect to x. Alright, so f of xy is equal to, so integrating e to the xy with respect to x, that's quite easy. That's just 1 over y e to the xy. The second term is not so easy to do in my head, so let's use integration by parts to integrate xy e to the xy with respect to x. So in this case, I'm going to be using integration by parts. F of x is just equal to x. G prime x is equal to y e to the xy. Here we'd have f of x, g of x, that's x e x y, minus integral f prime x, which is just 1 times g of x, so e to the xy dx, which is equal to x e to the xy, minus 1 over y e to the xy. Don't need the plus c here. So plus x e to the xy minus 1 over y e to the xy. Not plus c here, but plus g of y. This and this cancel, so you'd have f of xy is equal to x e to the xy plus g of y. Now let's integrate f of xy with respect... No, let's differentiate f of xy with respect to y here. So f sub y is equal to x squared e to the xy plus g prime y. And f sub y is equal to q, so this is equal to q, and by comparison here and here, that implies that g prime y is equal to 0. So in this case, that means that f of xy is equal to x e to the xy plus k, or c, or with some constant, yeah. So now we have our scalar function here. Now, let's say we're asked to evaluate or solve, let's say the question asks us to solve CF dot dr, where C is the curve, given by r of theta is equal to cos theta 2 sine theta. And theta goes from 0 to pi over 2. Well, we know that f is conservative. We've already shown that this vector field is conservative. So that means CF dot dr is equal to C, this gradient dr, which is equal to f of r of pi over 2 minus f of r of 0. So let's evaluate r of pi over 2 and r of 0 here. R of pi over 2 is equal to, so here is our vector function, r of pi over 2 is equal to 0 and 2. And r of 0, cos 0, that's 1, and 2 sine 0 is 0. So this is equal to, going down here, this is equal to f of 0, 2 minus f of 1, 0. So you can ignore the k in this particular case. So f of 0, 2, that's equal to 0 minus 1 times, minus 1, it's equal to negative 1. So this is the value of the line integral. Now let's suppose we have a 3D vector field. Let's suppose that our vector field f is equal to z e to the xz in the I direction minus z sine yz in the j direction plus x e to the xz minus y sine yz in the k direction. Now, how do we see if this vector field is conservative in 3D? Well, the test is to see if the curl of the vector field is equal to 0. If this curl value is equal to 0, then this vector field f will be conservative. So there's actually a formula for the curl of a vector field. So curl f is equal to, you're just going to have to remember this. It's going to take some time, but just put this through your head many times. dr dy minus dq dz in the I direction plus dp dz minus dr dx in the j direction plus dq dx minus dp dy in the k direction. So in this case, P, Q, and R are labeled right here. This is P, this is Q, and this is R. All right, so let's evaluate. dr dy is equal to, so integrating r with respect to y, that's equal to negative sine yz minus yz cos of yz minus dq dz. So minus and minus becomes plus, so this is plus sine of yz plus yz cos yz in the I direction plus, so let's look at dp dz now. So that's e to the xz plus xz e to the xz, okay, minus dr dx now. So minus e to the xz minus, so this would be xz e to the xz in the j direction plus, and lastly dq dx. So dq dx is 0 and dp dy is also 0. So 0 in the k direction. And if you take a look, the I, j, and k directions all have 0. So this is a 0 vector. And this means our vector field is thus conservative. So therefore, there is a function f such that the vector field is equal to its gradient. So now let's find this function f of x, y, z now. So p is equal to fx, which is equal to z e to the x z. F of x, y, z is equal to e to the xz plus g of y, z. Let's differentiate this function with respect to y now. So f y is equal to, so e to the xz, differentiate that with respect to y, that's just 0. So all you have is g sub y, y, z. And this is equal to q, which is equal to negative z sine yz, which is equal to q. When you integrate this with respect to y, you end up getting g of yz is equal to cos of yz plus h of z. And lastly, so this means that f of x, y, z is equal to e to the power of xz plus g of yz, which was equal to plus cos yz plus h of z. So now let's differentiate this with respect to z. So fz is equal to xz minus y sine yz plus h prime of z. F differentiated with respect to z, this is equal to r. So when you compare this with this right here, you get that h prime z is equal to 0. So this means that f of x, y, z is equal to e to the xz plus cos yz plus k. I'm going to just write this function on the side. So let's say we're asked to evaluate CF dot dr along the curve C, where C is represented by this position function r of t is equal to sine t, and 2t, and t ranges from 0 to pi over 2. So we know that this vector field f is conservative, so that means that CF dot dr is equal to C, this gradient dot dr, which is equal to f of r of pi over 2 minus f of r of 0. So let's evaluate these position functions. So r of pi over 2, r of t is right here. R of pi over 2, that's equal to sine pi over 2, that's 1 pi over 2 and pi. R of 0 is equal to 0, 0, 0. So this is equal to f of 1 pi over 2 and pi minus f of 0, 0, 0. Okay, so we have our f of x, y, z. We have our scalar function right here that we can just plug in x, y, and z. So this is equal to f of 1 pi over 2 and pi. So that's equal to e to the power of pi plus cosine, let me think, y times z, that's cosine pi over 2 times pi, minus 1, so e to the power of 0 times 0, that's just 1, plus cos of 0, that's also 1. So this is equal to e to the power of pi plus cosine cos of pi squared over 2 minus 2. And that's our final answer.